Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the energy analysis and the deviation for the Rankine cycle. All four components associated with the Rankine cycle are steady flow devices, and thus all four processes that make up the Rankine cycle can be analyzed as steady flow process. The kinetic and potential energy changes of the steam are usually small relative to the work and heat transfer terms and are therefore usually neglected. Let's firstly talk about the energy analysis of an ideal Rankine cycle. Then, the steady flow energy equation per unit mass of steam reduces to the boiler and the condenser do not involve any work, and the pump and the turbine are assumed to be isentropic. Then, the conservation of energy relation for each device can be expressed as follows. For the pump, we have this relation. For the boiler, we have this relation. For the turbine, we have this relation. For the condenser, we have this relation. The Rankine cycle is determined with the properties of T1, P1, and P2. The thermal efficiency of the Rankine cycle is determined from. The thermal efficiency can be interpreted as the ratio of the area enclosed by the cycle on a TS diagram to the area under the heat addition process. Now, let's talk about the deviation of actual vapor cycles from idealized ones. The actual vapor power cycle differs from the ideal Rankine cycle as a result of irreversibilities in various components. Deviations of actual vapor power cycle from the ideal Rankine cycle are illustrated in Figure A. The effects of pump and turbine irreversibilities on the ideal Rankine cycle are illustrated in Figure B. The fluid friction and heat loss to the surroundings are the two common sources of irreversibilities. Fluid friction causes pressure drops in the boiler, the condenser, and the piping between various components. As a result, steam leaves the boiler at a somewhat lower pressure. Also, the pressure at the turbine unit is somewhat lower than that at the boiler exit due to the pressure drop in the connecting pipes. The pressure drop in the condenser is usually very small. To compensate for these pressure drops, the water must be pumped to a sufficiently higher pressure than the ideal cycle calls for. This requires a larger pump and larger work input to the pump. The other major source of irreversibility is the heat loss from the steam to the surroundings, and the steam flows through various components. to maintain the same level of network output, more heat needs to be transferred to the steam in the boiler to compensate for these undesired heat losses. As a result, the cycle efficiency decreases. Of particular importance are the irreversibilities occurring within the pump and the turbine. A pump requires a greater work input, and the turbine produces a smaller work output as a result of irreversibilities. Under ideal conditions, the flow through these devices is isentropic. The deviation of actual pumps and turbines from the isentropic ones can be accounted for by utilizing isentropic efficiencies defined as. Other factors also need to be considered in the analysis of actual vapor power cycles. In actual condensers, for example, the liquid is usually subcooled to prevent the onset of cavitation, the rapid vaporization and condensation of the fluid at the low pressure side of the pump impeller, which may damage it. Additional losses occur at the bearings between the moving parts as a result of friction. Steam that leaks out during the cycle and air that leaks into the condenser represent two other sources of loss. Finally, the power consumed by the auxiliary equipment, such as fans that supply air to the furnace, should also be considered in evaluating the overall performance of power plants. Okay, that's all for this task. Thank you very much, and see you next time.